Recorded. Okay, so and then I'll go over any questions you have on any subject throughout the semester related to any topic on the final, any questions specific to the final, and then we will go over the review questions I've had posted for you under week 15. You guys can select that we solve together some questions, or if you'd like, we can go over each one of them. So we'll see depending on time. Some of them are kind of like more practice and repetitive, so it would be preferable to focus on a few. And I just want to remind you guys that some of these questions on the review packet will be on the final in one form or the other. So I just wanted to clarify that. Last thing I want to ask you guys is to please fill out the teaching evaluation. It would be great to have your input. And just to give you an incentive to do that, like you did for mid term evaluation, if you complete it and save a screenshot of you completing it or an email, I will create another extra credit for you to just put it on Canvas, and then we'll give you +2 on the final exam. So this way, it will be kind of an incentive for you to fill it out. The more responses we get, the better. Um, okay, with that, I'm just going to start sharing my screen here. Okay. Um, all right. Let's, like usual, let's do some recap questions. So, what are the different categories of residues we've talked about and contaminants of concern? Can you name a few? Unmute yourself or in the chat box. Nobody's willing to share anything. Drug residues, pesticides, toxins, allergens, sulfites, nitrites, heavy metal. Yes. Okay, so we have chemicals, including pesticides and antibiotics, heavy metal, sulfites, nitrites, and then you have the allergens, and you have adulterants such as melamine. That is correct, and then GMO is another category. So a lot of those. So everything you've said is correct. How would some of them get into the food? This is a typical question that might come on the final is name a contaminant of concern, how it made its way into food, and what would be a method of analysis. Okay, so how would pesticide, well, and during processing, so yes, we can generate acrylamide, for example, or add nitrate for processing of meat, transportation, where we can get contamination, yes, found naturally, antibiotics and residual in animals that got slaughtered sooner than they should be before stopping the antibiotics, or improper washing step, adding pesticides at a higher level um, than recommended. Yes, all of that. Um, and then some of the quantitative and qualitative method. Yes, Eliza. is immunoassays are common. A lot of the methods really for these contaminants are usually chromatography, liquid chromatography and gas chromatography coupled with mass spectrometry. A lot of these components are determined that way for quantification. For qualitative, you can do thin layer chromatography is one. For example, for qualitative, you can do NIR to determine presence or absence of melamine, for example. But yeah, but mainly you have chromatography and linked with mass spectrometry for quantification. Again, I want to remind you this is a good table to study, to look at all of the different components um, other than pesticides. And you have pesticides, antibiotics, and mycotoxins and toxins, and then allergens. So these are main kind of categories. And then you have the other components or contaminants of concern, and that's a good table to study. So it would give you an example for reason that they made it into the food, why is it of concern, and type of food and method of analysis. So if we look at melamine, we talked about it briefly last time. Has been used as adulterant in pet food and infant formula. Look at its molecular structure. It has several amine groups. So definitely in Keldal, these amine groups will count towards nitrogen and will be determined as proteins by a conversion factor. Also, all of these nitrogens, whether they're amine or non-amine, in Dumas method, it will be counted towards nitrogen and then it would be counted as proteins. So that was kind of adulteration to kind of increase the assumed protein content. And it's a fraud basically with to have a low cost and uh, have profit. But unfortunately, it has severe health consequences, mostly kidney infection, and can be fatal. So, um, yeah, so it shouldn't be there basically in the food. Main method of quantification, it can, like I said, GCMS. It could be GCMS, LCMS, and it's often linked to an MS in tandem. So for further quantification purposes and better detection and identification purposes. So you'll see a use of LCMS, MS as a method for detection and quantification. Other methods other than MS, we can do near IR or mid IR, coupled with Fourier transform, so FTIR basically. So that method can give you at least a fingerprint and identification of the presence of melamine. And not unless you do some sort of calibration, it might not give you accurate quantification. Immunoassays is another method or can be used as well for detection and quantification. Bisphenol A, we mentioned also last time briefly, it is present in plastic. It can be present in polycarbonate plastic specifically and can leach into your product or beverage. It does simulate hormones in the body, so it has negative health effects, especially on babies and children. Um, it's really this particular plastic is either banned in certain countries or permitted in lower amounts. Again, you have GC or LC or immunoassay coupled with mass spectrometry for detection. This is also another contaminant that could leach into the product, and it's from ink. So methylbenzophenone, And there has been contamination in cereal. And like I said last time, most cereal boxes in the product is inside in a plastic bag container rather than without a plastic container to avoid any leakage of ink into the product. Health concerns in children and LCMS as detection method. Furan, these can be formed during processing, especially at high temperature. They're carcinogens. Um, and again, they can be volatile, so they can be measured by headspace GCMS. Acrylamide is another chemical that can form during processing, but this forms mainly in high carbohydrate foods with high temperature in the presence of some proteins. So specifically amino acid asparagine is the amino acid that reacts with reducing sugar to give you this metabolite, which is acrylamide, and it is a carcinogen. Again, chromatography with mass spectrometry as method of detection. Benzene is another carcinogen. It can be present in some beverages. For example, if you have beverage with benzoate salt and ascorbic acid, you can form benzene. It is volatile, so headspace by GC and coupled with MS. Monochloropropane, this is formed when we hydrolyze proteins to produce hydrolyzed vegetable protein. So what happens is when you use HCl to hydrolyze, and if you have any residual fat, the residual fat will react with HCl and give you a monochloropropane product, which is a carcinogen and genotoxin. It is volatile, so it can be analyzed by GCMS. Percolate, the last one I have here, it can be, it is actually byproduct of rocket fuel, and it can reach water, milk through the cow consuming some of um, the grass that might have this contaminant. And it has been found in lettuce as well. It has been reported to be found in lettuce. So LCMS, MS is a method for detection. So that's all for contaminants. So I will wrap this up with about a very short section on, let me get out of here, and then go to the last topic, which is kind of related, which is extraneous matter. So let me, okay. So what does extraneous matter mean when you hear the word extraneous matter? What kind of extraneous matter you might find in food? Yes, hair, animal hair, rodent hair, insects or insect fragments, um, and yes, all this, any animal related matter, metal, glass, soil, um, yeah, all of that is extraneous, meaning it shouldn't be there. It's in the food and it shouldn't be in there. So rodent hair is very common because rodents are everywhere, especially in storage warehouses. It's really not avoidable. It cannot be avoided. Insects are everywhere as well. So a lot of like either whole insects or parts of insects, uh, the feather um, material from birds, stone, sand, dirt, metal, glass, plastic, anything that is not supposed to be in food and not consumed, we shouldn't consume, is considered extraneous matter. So there is kind of this controversy about insects being part of the extraneous matter, and now in many countries, not now, for many, many years, it is food. And now we also look at insects as sources of protein for protein ingredients. So this is kind of a controversial topic at the moment. How are we going to introduce insects and insect proteins when by FDA they are recognized as extraneous matter? So it is a subject of debate. So so in the field we can get insects or rodents and storage, during transportation, during processing. So of course, insects are everywhere. So when we harvest the crops, you're going to harvest some insects along with them. And during storage, there is rodents everywhere. It's kind of like you cannot completely avoid rodents. So we have a Food, Drug, and Cosmetic Act that states that food is adulterated if it contains filth, putrid, or decomposed matter. Ways to kind of control it is by good manufacturing practices, GMP, where we process under sanitary conditions to make sure as much as possible we don't have infestation, we don't have dirt. We follow a thorough inspection of raw material. So among the quality tests for, grains or flour that come into the manufacturing facility, one of the tests is extraneous matter, and they would be rejected if they contain extraneous matter above the defect action level, DAL. So you can see that they're unavoidable. So we have defect action level. You might be surprised to know that it's okay to have 30 insects fragment and 1 rodent hair per 100 grams of peanut butter. So think about it, eating peanut butter enriched with insects. So it adds to the protein. Look at the flour, for example. 50 grams of flour is like, it's just like a little bit of flour. 75 insect fragments is allowed and 1 rodent hair. Above that, then that's not allowed. So again, more sources of protein, I would say. This is a joke for you guys. We'll skip that to save time. Terminology. So filth, animal contamination, or other objectionable matter. So you will hear these terms. So you hear filth, you hear heavy filth. What heavy filth means, those that would sediment. So soil, sand, excreta pellets from rodents or insects, so they can be separated by sedimenting. Light filth are oleophilic. That means they would remain with the oil or fat. They or can be associated with an oil layer, and they're often separated with using oil, and they float. So that we use oil and flotation to kind of separate and count them. So small insects, insect fragments, rodent hair, feather parbulas. So these are light filth. The sieved filth is anything that you can separate using sieves. And usually you use 20 mesh size sieve, sorry. So a lot of concerns with identification, detection, and determination of extraneous matter. First of all, you want to have experience recognizing these parts. For example, mandibles. So this is of an insect, is easy to recognize. But if you have insect cuticle, which is part of the exoskeleton of the insect, you might not recognize it as insect fragment. So it requires training and experience to be able to recognize and count them towards fill. The methods that are involved require a lot of filtration and transfers, so there could be losses there. And not often, it is based on counts. And you count regardless of size. One insect counts as one, and one fragment of an insect counts as one. So, and you have different sizes of insects, obviously. So that is also of a concern. Um, so I'll go over a few methods, examples. For example, here, anything powder form like spices and condiments. So these, if you want to measure filth, it's basically very simple. You use 20 mesh size sieve. You just sieve the sample, and then whatever is left on the sieve is you just look under the microscope and count. Basically, you count, and then you know the weight of the sample, so you can determine the count per certain amount of sample. Another method here is AOAC and AACC approved. Filth in shelled nuts. So what you do is you extract with an organic solvent, petroleum ether, chloroform, and carbon tetrachloride. So it's a combination where the shelled nut will float to the top, and then the heavy filth will sediment. So the heavy filth meaning any soil or dirt you have, or shells still that you have, and they're not supposed to be in the shelled nuts. Um, so filter the sediment and use ashless filter paper. You can either count under the microscope, or you can ignite or ash. That means in a muffled furnace at 500 degrees C, and then you weigh the ash, because these are inorganic matter. And a common method, for example, used in flour, and in this case rye flour, is to determine insect fragments and rodent hair. So in here, you digest everything with acid, and you would use an oil, and tween and EDTA are added so that any fiber material doesn't float, it sediments, it remains in the lower compartment. Here you use Wildman trap flask, where everything that's digested with acid and would remain in the aqueous form, and then there you will have an oil layer. You kind of use kind of a stopper that you lift up, and then you trap the oil in the upper neck, and you transfer and you filter using a Buchner funnel here with a filter paper, and you just count under the microscope. Can remember that insect fragment, rodent hair are light, so they're light filth. So they and they are lipophilic, so they like the oil. So they will be in this phase, the oil phase. This is post milling of a flour. They call it flotation method. It's another method for light filth. Again, digestion with acid using mineral oil. You can use a separatory funnel in this case, and your aqueous phase will be at the bottom, and the oil phase that has less density would be at the top. You just separate them, filter again, and count under the microscope. X-ray, these are for insect infestation in kernels. So this is wheat kernels. So you can see the larva of the insect inside of the kernels. And it is okay to have about 30 kernels in 100 grams that would have insect. That is the defect action level. So X-ray is used to determine this infestation and count the number of infested kernels. It's not an official method of analysis, the X-ray is not, but it is commonly used as a preventative measure for the amount of insects that wind up in your flour. Another method for measuring presence of filth is measuring uric acid. So it is basically in the urine from insects and birds, for example. ELISA, measuring the protein, myosa, which is specific for insect. Um, Near infrared for determining infestation of wheat. And then you have microscopic techniques to detect metal types, whether you have glass, plastic, or other crystalline contaminants in your food. Preventative measure, X-ray is preventative. So you would count under how many insects are damaged. Per 100 grams, you're allowed 32. You can prevent a lot of insects by aspiration, so blowing air and light insect fragments, rodent hair, and light filth basically will be blown off. Air flotation, so if you have grain, light grain, and you put them on a belt, and the belt is porous, you have air from underneath the belt, the grains will float, and what remains on the belt if you have dirt, so heavy filth basically, and excreta. So they would remain on the belt, and you can separate them that way. You can break the kernel and follow by air blowing to remove any insect parts, and use magnets to remove any metal contamination. So that's all for lecture material. So basically we're done here with lecture material. We can start the review. Any questions before I start review? Any concerns, questions that anybody might have? No? You're all good?
I just have a question for like in the exam, would it be okay to write like BPA and like 3 MCPD instead of like their full name? Does that make sense? Like when we mention contaminants.
Yeah, it's okay to give abbreviation. That's fine. Any questions other than that on for the exam, for the final? Any topic you'd like me to clarify? Okay then. Please don't be shy. Ask questions. This is kind of your chance of doing that. Let me see.
Pam,
Yes.
question.
Yes.
So, when you're asking us to write down the procedures for measuring total dietary fiber or soluble and insoluble fiber, like should we write down everything that you said in the slides, or is that a way to write it?
You don't have to write everything in detail. So let me pull that up because I have that up because I knew that you will have a question on that. So here you go. I was ready. All right. So I know there's a lot of detail that you see here, but I would like you to remember, you don't have to remember adjust pH, buffer, heat sample, gelatinize, control pH, temperature. No, these are details. What I'd like you to know though, that you have to separate everything from the fiber. And in order to do that, you have to hydrolyze. So you have to hydrolyze the starch, you have to hydrolyze the protein. So you have to remember that because then these will remain soluble with any other soluble sugars that you have and all of that. So when you hydrolyze everything and they remain soluble, and if you add ethanol, your soluble and insoluble fiber will precipitate. And you can get total fiber that way if you add ethanol at that step. If you don't add ethanol at this step, what you would do is you would filter. Then you would have your soluble fiber with the solubles, with everything that was soluble. And then you would have the residue, the insoluble fiber. So the insoluble fiber, you just filter, you wash, and you dry, and you weigh, and you get your total, you get your insoluble fiber. To get the soluble fiber, you take everything that was soluble. And at that point, you would add ethanol, then the soluble fiber will precipitate and everything else will remain in solution. Your amino acids, your sugars, everything remain in solution. and your soluble fiber will precipitate. You wash, you dry, and then you get your soluble fiber. So now you have insoluble fiber and you have soluble fiber. One thing you want to remember is we always correct for ash and protein. So you would measure ash and protein and subtract the weight of those. So then you get your actual soluble fiber and actual content of insoluble. Add them, you get the total soluble fiber. So the general overview, basically, Jean, does that answer your question?
Yeah.
Okay. Any questions similar to that in terms of what details you need to know? No? Don't be shy. This is the time to ask. Okay. No questions? All right. So before I go into these questions, I'm going to ask you fast questions first. I would like your participation. You can unmute. It would be nice to unmute yourself so that we kind of have a conversation rather than reading. But you can type as well. So I'm going to say the name of the method, and you're going to tell me what this method analyze or test for. Okay? So CalDOG.
Protein.
Protein. Yes, thank you. Moginer or Mojonier.
Fat.
Fat. Titratable acidity. What are we measuring?
Acidity.
Yeah. Organic acids in food. Yeah. Organic acid in beverages and food product. Yes. Babcock. Do you remember?
Protein.
Milk fat.
Yes.
Fat.
Yes. Fat in milk. Vollard. VOLHARD. One of the recent topics we talked about.
Reverse titration for chlorides.
Yes. Reverse titration for salt. Yeah. Very good. Let's see. Peroxide value. What does it measure?
Primary fat oxidation.
Primary oxidation.
Primary oxidation, yes. More, MOHR.
Forward titration.
Yes, it is a titration for salt determination of NaCl. Goldfish.
Fat. Fat.
Fat. Soxhlet.
Fat.
Fat.
Fat. Let's see, Carl Fisher.
Moisture.
Content.
Moisture content, yes. So folding number, Suzanne Nielsen mentioned it in her lecture. Does anybody remember? Anybody at all? Okay, it doesn't ring a bell. All right, so in flour, in order to determine the presence of alpha amylase, because alpha amylase impact the viscosity of starch, when we hydrolyze, if you have alpha amylase endogenous in your wheat that is present at high amount, it's going to hydrolyze the starch and the viscosity will be reduced. And that will impact functionality. So falling number, basically what you do is you have your flour, you add water and you homogenize. And what you do is you put in a plunger and measure the falling of that plunger over a specific period of time. And they call that the falling number because it can be related to the alpha amylase activity.
Is there, for that falling number, is it the more alpha amylase activity, the less viscosity?
Yeah, so with lower viscosity, the plunger will fall more, and that means you have higher alpha amylase activity. Yes. Okay, muffle furnace.
Ash.
Dry ash.
Yes. Quantab strips. We mentioned them again in a couple of lectures ago.
Is it with the more titration?
Yes, it's more titration for salt. So it's based on more titration, but it is test strip. So it's a quick measure of salt. Charm tests. We talked about it on Monday. Anybody remembers?
Is that milk?
Yeah, something that has to do with milk. What are you testing in milk?
Draft?
I love the background, by the way. Okay. We are testing antibiotics. So you would have a radio-labeled antibiotic that competes with the antibiotic in your sample. And the more the radioactivity that you can measure, the less the antibiotic that is in milk. So that's kind of a charm test, they call it. Monnier-Williams, we talked about it also last Monday. It's the most common test for measuring sulfites in food. Nitrogen combustion or DUMAS.
Protein.
Protein. Okay, so now I'm going to state few tests and then you're going to tell me why we test those in food. Why do we measure alkaline phosphatase in milk? Again, Suzanne mentioned that in her lecture. Anybody remembers anything? To test the effectiveness of pasteurization. So it's a very thermally stable enzyme, but when we pasteurize, if it's inactivated, that means the pathogens have been killed because it's more thermally stable than pathogens. So instead of having 2 days of micro testing for pathogen, you just measure the activity of alkaline phosphatase. It's a very common method that you would determine whether the milk was efficiently pasteurized. Let's see. Peroxidase in vegetables. What do we, when we measure peroxidase, what are we really, during processing, what are we really looking for? Effect of blanching, because when you blanch, you inactivate enzymes, and peroxidase and lipoxygenase are the most thermally stable, among the most thermally stable enzymes. So if you measure peroxidase or if you measure lipoxygenase, you can determine the effectiveness of blanching. Why do we measure antibiotics in milk? What's the limit of antibiotics in milk?
No antibiotics allowed.
No antibiotics in milk. We shouldn't have those in milk. Why? Does anybody remember why?
Antibiotic resistance or the zero tolerance, I don't know.
Yes, antibiotic resistance can be developed. Also, some people are sensitive, have allergic reaction to antibiotic. And if there are antibiotics in milk that is meant to produce yogurt or to have cheese for during ripening, you might have inhibition of needed bacteria. So that's why we shouldn't have any antibiotics in milk. Why cows are given antibiotics if they're not sick? If they're sick, it's known, yes, but if they're not sick, do you remember? As a preventative measure for not getting sick and also to help with weight gain. And they stop giving them antibiotic as time gets closer to slaughter or for lactation. Okay, so So these were my quick, I have posted key for almost all of the practice problems, for proteins, for pH and titratable acidity, for the fiber question, and I don't remember what else, but I did not post a key for fat characterization. Would you like me to go through these questions with you? Yes? No? Yes, it would be helpful, I would say. Okay, let me go to, where was the fat characterization? All right. So when you have soapy flavor in a snack that has been fried in oil, what could this flavor be due to? Soapy flavor. What do you think happened when you're frying? So you have water from the food, and then you have the oil, and then you have heat. Prior to lipid oxidation, yes, you might get lipid oxidation for sure.
Free fatty acids.
Hydrolysis.
Yes, free fatty acid formation. Yes, so breakdown of not quite saponification because you don't have alkaline added. So it is just there is hydrolytic breakdown of the fat. So you generate free fatty acids. So you test the presence of free fatty acid by titration, like we do for titratable acidity, like you did in the lab. And you do test for oxidation as well, just in case, because free fatty acids are prone to oxidation more readily than a fatty acid in a triglyceride, so esterified fatty acid. Okay, so let's look at another fried snack food is stored in a warehouse, and you go in and you have an odor, painty, fishy odor. Why do you think? What could have happened here? Most likely during storage.
Secondary oxidation has taken place.
Oxidation, lipid oxidation, yes, for sure. So if you do have these snack food packaged in packages that are permeable to oxygen, if you have light, if you have high temperature during storage, then potentially you have lipid oxidation. So you want to measure for oxidative rancidity. You can do peroxide for primary oxidation, and most common for secondary oxidation is a hexanal test. So that's a very common method, which is by headspace GC. All right. So the answer is in the question here somehow. So you have raw wheat bran. So you have a cereal product and it has raw wheat bran. I don't know how much you know about the wheat kernel and where the enzymes are, but most enzymes, lipase, lipoxygenase, are present in the bran and germ. So you have a lot of those enzymes there. And if you have high bran and germ and they are not preheated, then you have lipase that could lead to hydrolysis of the fat, and you have lipoxygenase that could lead to oxidation of that hydrolyzed fat. So we test for both free fatty acid to determine lipase presence of YouTube lipase presence potentially, and we do look at peroxide or other secondary metabolite of oxidation. Question 4 is a common question that might show up anytime. So if you want to determine oh, I see. I think this question actually, I've asked it the very first lecture in food analysis, if you remember here. So you have a cereal-based pellet sold to customers, and the customers process these. Let's say they fry them, they package them, and then now they have a complaint that they're rancid. So they come to you as a supplier and say, okay, we have an issue with that product. So what would you do to determine the problem? To determine if the problem is your problem or the problem is out of your hand? What would you do as an investigator? So you're trying to investigate a case here. Anybody?
Would you first want to determine whether or not it was hydrolytic rancidity or oxidative rancidity?
Yes, it's okay. Well, you have rancidity, right? You have hydrolytic rancidity potentially and oxidative rancidity. But if you want to determine the cause, so as an employee of the supplier, you want to defend your product, right? So what would you do? So you would take samples of your own product, and then you tell them, give me a sample of your oil, give me a sample of your packaging material. And then you assess if the oil is oxidized, if you have free fatty acids and oxidized fatty acids in the oil, if you have free fatty acid and oxidized fatty acid in your snack, in your product that you sell to them, or if there is, your packaging is permeable to oxygen, that would cause that issue. So it's a case where these cases actually happened in industry, and these examples come from industry, that you have to do kind of a forensic type of investigation if you work in industry and you want to defend your product. So in question 5, you have developed butter with fish oil. Of course, fish oil has high unsaturated fat. So before placing the product on the market, you need to determine its shelf life. And sometimes you need to add antioxidant as well to it, and then determine the shelf life. So how would you determine the shelf life of this oil butter product? Remember in class, we talked about 3 methods. If you remember, one of them is good.
The oven storage method.
Yes, oven storage method. So basically you want to abuse the sample at high temperature so that you can, instead of storing it for a long period of time, you can assess its shelf life by accelerated storage. So you put it in an oven at 60 degrees, and then you'd start taking samples at several time points and determine the formation of peroxide value, for example. Then you would know the induction period. That means the time it took until you saw an increase in peroxide value from beginning, from the 0 time. So you can do that. There are 2 other methods, which is the oxygen bomb method and the oil stability index method. So whatever you feel comfortable remembering, but as long as you remember that you choose one of these methods, and then you have to say that, okay, I will measure peroxide value over time and determine at which time my peroxide value will go up. So that's important. You don't just list the method, but just continue saying what you would do. So you would have a protocol and a peroxide value to measure over time. Okay, so the last one here. So you're making peanut butter. I work in a quality control. You received information in a certain period of time that several lots of the peanut butter have been improperly stored. and you're concerned about potential lipid oxidation in the product, you have a total of 50 lots of peanut butter involved. Okay, so this is a case where you have to remember, okay, I have 50 lots. And we talked, that's where sampling, chapter 5 in your textbook is kind of essential throughout, because you want to know, okay, do I measure every single sample? It's a lot, 50 lots. And then within each lot, you have so many samples. So you want to randomize and select few lots. And within each lot, you would select a number of samples randomly, and then you would want to test, okay? So sampling is very important to remember that you need to have a sampling plan. And from there, you test peroxide value and hexanol at least, or any other secondary metabolite of oxidation, because again, if peroxide value is low, it doesn't mean that you don't have oxidation. Yeah, so the question B is, how do you decide? It really depends on how many samples are defective. So you just have to go with the rules based on how many lots you have, how many samples you tested, and based on how many samples were defected, you want to make sure you have 5% risk to consumers when you accept versus reject. 10% risk to producers and 5% risk to consumers. Okay, any questions regarding this review? Okay. Please, if you think of any question, why would oil be used?
I was referring that to the pellet thing. Like, why would you?
Oh, if it's a fried snack.
Okay, makes sense.
So usually you provide the pellet and then they process it. And fried snack and they package it. Yeah. Okay. Any other questions before we move on to the review set of questions? So in the review set of questions, you'll see that we have about 15 different questions. We will not physically be able to go through all of them. We can prioritize and see how much time we have, and we continue going over. So I can tell you for sure that question B here is for you to practice. You basically have these equations in your laboratory addendum in the proximate analysis. You just want to remember how to do these calculations. Basically practice, okay? So we're not gonna do this together here. This one, the first one, 1A, again, this is reminding you that sampling plan is an important thing for you to remember. So I cannot say that enough. So you just have to, remember, because when you go out to industry, this might be part of your job. So you really want to know that sampling is important and how to get representative sample. For all of the analysis we talked about throughout the semester, if you do mistake in sampling, the error is huge in terms of decision making. So you want to remember that. So when you have 10, let's say 100, so not 10, it should say 140 pounds bag. Sorry, it's my fault. So 140 pounds bag. So let me save this for later. So you have 40 bags flour and you have 100 of those. You're not going to measure, again, test all of them. Usually you take the, yeah, I know, sorry, it should supposedly say, I might have 100 multiple versions here. It should say 140 pounds back. So, so this 140 pound bag, usually the safest to say is you take the square root of the 100. So if you have 100, you take the square root of that, That's 10. So you would number your bags random numbers, and you would use a random number table, and you select 10 random numbers, and from there you take these bags. And then also, if you, of course, you don't remember, I'm going to show you here. Let me bring this. So there is an example for flour bags here. So when you select your flour bag, you would take 2 samples from 2 corners to the center, opposite to each other. So you take 2 samples from each bag, and then you analyze. That is your sampling plan.
Hey, Pam.
Yes?
I have a quick question. Are we allowed to ask about any of the format on the final, like how many questions it might be?
Yes, for sure, you can ask. So the format of the final is basically very similar to these questions that I have. So you'll have a set of questions with subsections, just the same as these, but definitely not 15 questions. So let me, okay, I can tell you because I have the final in front of me. So that you prepare yourself. There are going to be 7 questions, but the last 2 questions, 6 and 7, you would select to answer one of them. So the last 2 questions, I give you an option to select the one that you're more comfortable with, and you would answer. So basically it's 6 total questions with subsections underneath each question and 1 bonus question. The bonus question.
So there aren't any multiple choice like the quizzes?
No multiple. They're all short answers. And I can tell you now so that you can be prepared, there will be about 3 or 4 calculation questions. And you would want to have a piece of paper or 2 pieces of paper next to you and a calculator. And then at the end, you take a picture of those. You have to enter the answer in just the answer on the Canvas test, and your answer should match the answer on your calculation sheet. And we'll give you time at the end to attach the calculation. So we're doing this live so that you don't worry about time. We'll make sure that you're able to finish and attach your calculations at the end. Okay. Any other question about format or exam? Okay. All right, let's go back to this. Yeah, like I said, question 1B is just practice your calculation. Also, I want you to be able, I can't remember now, and I'm not gonna give this away, but there might be a question that tells you make up your own values. So I won't give you values or weights of sample or weight of dish or weight of anything. I'll just tell you make up your values yourself. So you just want to make up numbers that are easy for you to use to calculate. Don't use decimal points, for example. Just pick numbers that are easy. But you need to remember in SOCSLID, for example, what are the different weights that you've taken? There was the thimble, the weight of the sample. Then there is the weighing after the extraction. So if you know the order of things, then you can just make up numbers for each step and come up with a reasonable percent fat. If it's in cheese or flour, what would be a reasonable percent fat? So simplify things for yourself, but you really need to know the method really well to make up numbers. Okay. So here, this is a common question that you might get. To determine iron content, would you use the ash obtained from dry ashing? Or would you rather follow a wet ashing procedure? What would you say, guys?
Wet ashing.
Yeah,
Yes.
wet ashing.
Wet ashing, yes. So the dry ash, really sometimes you have to remember iron is one of the minerals that are volatile, right? And if you want to determine iron for the label, you have to be as accurate as possible. You cannot afford losing iron by volatilization during ashing. You need the dry ash value so that you can get total carbohydrate. You have to have the dry ash value. But if you want to get the iron and be certain about the iron or zinc or any other volatile, you want to do wet ashing. Because wet ashing is done at about 200, 230 degrees Celsius in highly concentrated acid. So you do all of the oxidation and combustion of organic matter, but your minerals remain in solution with the acid, soluble with the acid, and does not volatilize. So just remember that. Here you want to remember your official methods of analysis. You don't have to list Soxhlet and Muginer for fat. Just remember one of them that you're comfortable with. Same with protein, Dumas or Kelda. And when I say briefly, really what I mean is just like a couple of sentences that kind of gets the gist of the method. So Dumas, sample is combusted at high temperature, or gases get scrubbed off, nitrogen oxides get reduced to nitrogen. You don't have to remember that. Just say nitrogen then is analyzed by thermal conductivity detector. So combustion at high temperature, all gases get scrubbed, nitrogen get analyzed by thermal conductivity detector, and then use a conversion factor to get to the protein. If you use Kelda, sample is digested with a concentrated acid, distilled with a base, titrated with an acid to get the nitrogen content, which is then converted to protein. Okay, so moisture, if you decide to use vacuum oven, the sample is weighed, placed in that under the vacuum oven. Moisture is then evaporates at low temperature, and then you take the weight after. The weight difference is the moisture content. Okay, so as simple as you can think of, as long as you give the gist to the method, you give justice to the method. All right. This is similar to what you guys got on the quiz, last quiz. What are the preparatory steps for carbohydrate? So really, you have to, it's two main steps. You dry, you defat. So that's the first thing you have to do. And after that, if you are, it depends what you are measuring. If you're measuring small sugars, then you have to say, okay, I'm going to extract with ethanol, 80% ethanol to get the small sugars. Okay, so you have to be careful reading the question and see what the question is really asking you. Here, all I'm saying is removal of moisture and fat to prevent interference. That's it. Okay. So what methods would you use to measure total starch, total gelatinized starch, total retrograded starch? You won't get all of these questions in one question, okay? Here is for you just to try to know what to study for, okay? You won't get all of these questions. I will make sure you have a reasonable amount of questions, but this is for you to know, oh, I need to study how to get total starch, and I need to study how to determine total gelatinized and total retrograded starch. You might get one, you might get two, you might not get that question, but just that you're prepared. So again, here I have that lecture up to tell you what I'll be looking at for starch. Really, for starch, you want to say that you hydrolyze starch to glucose. You want to say that I use alpha amylase and glucoamylase. So glucoamylase to break into singular glucose, but the alpha amylase is to break up that big starch molecule. Then you get glucose, and you want to say that I would use the two-step enzymatic reaction, glucose oxidase and peroxidase. So you want to remember the reactions. When I say chemical reaction, I don't say really you have to know the structure. You can just say glucose. In the presence of glucose oxidase, you get a peroxide. The peroxide reacts with a dye. You don't have to remember the dye. It just reacts with the dye. It oxidizes the dye, and then you get a color. Okay, so when I say chemical reaction is if you just say what the components that are reacting, you don't have to remember, for example, the name of the dye. You don't have to remember the structures. So again, it's a matter of knowing the principle of the reaction. So for gelatinized and retrograded, it's the same method. You just have to remember you use the same method. In this case, you use these two specific enzymes because they don't act on raw starch or retrograded starch. So if the starch is gelatinized, then these two enzymes will work. This is going to debranch, pollinase is going to debranch, and beta amylase is going to break it into two glucose units, give you maltose and maltotriose. These are reducing sugar, and then you can measure the amount of reducing sugar formed by Smoothie Nelson, for example. So again, just briefly the principle. Both, you would say both are measured by the same method. These enzymes only act on gelatinized starch. So the higher the gelatinized starch, the more reducing sugar I have. The higher the retrograded starch, the less reducing sugar I have. Please, if you have any questions, don't be shy. Just interrupt or type in the chat as I move along if you have any clarification question. And also just that you remember this Friday, my office hour 8 to 9, I'll be there. Last time I had Rachel cover for me, but I'll be there this Friday if you have more questions. And if you need to talk with me longer than that, let me know and I'll try to make time for you before Saturday. Okay. Let's see. This is the question that Jean asked at the beginning about total dietary fiber, soluble and insoluble. Yeah, we already covered that, so I'll move on. You will get an oil question. Let me tell you for sure, okay? We spent a lot of time on fat characterization, and we had a very nice lab on fat characterization. That was our last lab before Thanksgiving. So this is an important question. So when I ask, okay, so there's olive oil here. You measured the saponification value and you measured iodine value. So you want to state the principle of saponification value and show chemical reaction. Again, when I say chemical reaction, I don't mean structure. I need you to remember that we took the triglycerides and reacted it with 3 KOH molecules. So 1 mole of triglycerides reacts with 3 KOH molecule and gives you glycerol or fatty acid salt. So you don't have to even remember the second side of the reaction. I just want you to know what reacts with what. This is important. So you have 1 mole of triglycerides reacting with 3 moles of KOH. You've got to remember that. And you have to state the units. So saponification value is what? Milligrams of KOH that saponifies 1 gram of fat. So you gotta state that. And you state the reaction, what happens in that reaction. And why is it important? It's a characteristic assay. So it is very unique to the different oils, and it allows us to determine the average molecular weight of the fatty acids within the triglycerides. So that's the significance of the method. Okay, if you remember the units, then you can solve. If you remember the units and you remember the reaction, then you can solve this question. Did anybody solve this question? Does anybody have an answer?
I got 214.76.
Yes, that is correct. You can see I gave you all of the given that you need. If you remember the units, and it's already in the question, milligrams of KOH per gram of oil. So you have to remember your derived equation. This is the derived equation, we use it everywhere. The derived equation at equilibrium, right? To get a mass. So you would just, or a milli equivalent. So you have the volume of the titration used, you have the normality, and you have to remember that the blank is higher than the sample, because when you don't have triglycerides, all of your KOH remains, and you need to titrate all of it with HCl. Just a second. Okay, so you subtract the volume for HCl for the sample from the volume of HCl for the blank. You multiply by the normality, and then you multiply by the molecular weight. So I either give you the KOH molecular weight or I give you the different elements. So 56 or 56.1 if I gave you 56.1. And you divide by the sample weight, and you don't multiply by 100, and you do not divide by 1,000 because it's milligrams. So you do not correct milliliters to liters. So there is no division by 1,000, and there's no multiplication by 100 because it's only per 1 gram of sample. And then you get your value. Any questions there? Perfect. I'm seeing that folks got to that same number. Okay. So the question that comes next was your value within the range stated on the specification sheet? So the specification sheet, what did it say? It says 184 to 196. So the value was not the same. What does that tell you, potentially? It's olive oil sample, right? What does it tell you?
It's adulterated?
Yes, olive oil case adulteration is very, very common. So it could be adulterated with an oil that has higher or lower molecular weight average, fatty acid average.
Lower.
Lower, thank you. So with the higher saponification value, you have lower molecular weight, right? Because in 1 gram of fat, you needed more KOH. That means more molecules were there in 1 gram of fat. So then these molecules have lower molecular weight. Okay. And this is the question where I say calculate the average molecular weight. Did anybody do the calculation? And I give you the actual saponification value of olive oil. So did anybody get any answer here?
I got 282.6.
Yes, 282.6 or 282 is fine. And this is the molecular weight, actually, the average molecular weight of oleic acid. So here you really have to remember how to get the molecular weight of triglycerides. So you have to remember your equation. Let me go back here. Fat characterization, where is it? So here you really have to remember that you have 1 mole of triglycerides. Again, you don't need to remember the structure. Just 1 mole of triglyceride reacts with 3 moles of KOH. And you want to solve for the triglyceride molecular weight. So 1 mole of triglyceride, what would be the molecular weight of 1 mole of triglyceride? That reacts with 3 moles. So that means 3 times 56 grams per mole, okay? And then you have given, you have to convert the 190 to 0.19 grams because you want to make sure your calculation is in 1 gram. And you know that the given is reaction of 0.19 grams to 1 gram of fat. Then you just solve for your X, right? So it would be 3 times 56 over 0.19. And you get 884, which is the molecular weight of triglycerides. The other thing you have to remember, let me see here. Let me see if I can draw something. Where is it? Hold on. Okay. All right, so what you have to remember is you have the triglyceride plus 3 H2O molecules, water molecules. If we break them, then you get glycerol plus 3 fatty acids. Never mind, 3 fatty acids. So the triglycerides molecular weight we got is 884. I'm going to give you in the exam, if this question comes up, I'll give you that the molecular weight of water is 18. So then you go plus 3 into 18 equal, I'm going to give you the molecular weight of glycerol plus 3 fatty acids. This is essential to remember, right? Once you remember this, then you know I'll give you the given. I'll give you this 18, I give you 92, and you have that from the other equation that you just solved. Then you can determine the 3 fatty acids. And basically, it would be 1 fatty acid when you do the math would be 282. Okay, any questions there?
Where are you getting the 884 from?
884?
For your triglycerides?
Yeah, so we got that from the beginning when we said 1 mole of triglyceride reacted with 3 moles of KOH. That's your original chemical equation that then gives you glycerol plus 3 fatty acid salts, right? You remember that, you have to remember that. You have to remember that 1 mole reacts with 3 moles of KOH because 1 triglyceride has 3 fatty acids, triglyceride. So in saponification, you break down the glycerol into 3 fatty acids. So you need 3 moles of KOH. So you just have to remember that principle. And then 1 mole, how many grams is in 1 mole? That's the molecular weight that we don't know. So we're solving for X here, but we know the molecular weight of KOH. And I have given that for 1 gram, I needed 0.19 grams of, this is grams per mole, so that you remember what these numbers are. All right, so then you know that 190 milligrams per gram of sample. So 190 milligrams of KOH per 1 gram of triglyceride. So you just want to convert that to grams because you want to make sure that you're solving in grams. And then you solve for X here. So this is 3 times 56.1 over 0.19. This gives you the 884. Yeah, sorry. Irene, you got that? 884 grams per mole. Okay, is this clear for everybody now? Okay. If you intend, okay, let me get out of that. Discard. If you intend to hydrogenate the olive oil, if your version says corn oil, I meant olive oil. If you intend to hydrogenate the olive oil, would you measure iodine value again after hydrogenation step? Would you do that?
Yeah.
Yes, you would. Because iodine value is a measure of degree of unsaturation. And when you hydrogenate, you're saturating your oil. So you really need to measure iodine value to determine the completion of hydrogenation. Would you want to measure trans fat content?
Yeah, because the if you don't fully hydrogenate the cis, you won't get the cis conformation.
Yes. So if you don't fully hydrogenate, some of the cis will become trans. It's more stable form, and that has health implications such as heart disease related implications. So we do want to measure trans fat because incomplete hydrogenation might lead to trans fat formation. So if you need to measure degree of oxidation, which method would you use? Name at least 3 and explain the principle of each. I'm not going to ask you for 3 really. I just want to make sure that you study the at least 3. But in this case, you can say, I can measure peroxide value for primary oxidation. I can measure hexanol for secondary oxidation. I can measure T-bars, thiobarbituric acid reactive substances. Just remember it as T-bars if you want. For again, secondary metabolites. And remember a brief principle of each. Any questions there?
Can you just define like what an example of a principle would be for that?
Yes. So if you say peroxide value, so how would you determine peroxide value? So let's go here. And now let me simplify what you have on the slides. So the more peroxides you have, you more you have iodine produced because you react with potassium iodide. These methods you did in the lab. So I really want you to remember kind of like what reagents you've used. You don't have to remember structure or chemical structure. Just say that peroxides will react with potassium iodide to give iodine. The iodine will be titrated in the presence of an indicator. And the more iodine you have, that means the more peroxide you have in the sample. And peroxides are measured as milliequivalent per kilogram of sample. So another one, hexanol, is very simple. You just say that it's a volatile metabolite. You do headspace GC for detection. T-bars is basically you react the secondary, if you have secondary metabolite, it will react with T-bar, or TBA actually, it's the thiobarbituric acid. So it will react with TBA and then you measure absorption. So here's a question about protein purification. So look here, I gave you a hint in the question. So I gave you 3 different characteristics. I gave you molecular weight, I gave you isoelectric point, and I gave you a net charge. And then I said, this is the protein that we need to separate. So you need to state 3 sequential processes of separating these proteins. You can start by saying, I will precipitate at pH 5.2, collect the precipitate. All right, the precipitate might have proteins with similar charges and might have proteins with similar molecular weight. Then I can do size exclusion chromatography, followed by anion exchange, or I can do anion exchange chromatography followed by size exclusion. It doesn't matter the order. But in this case, I'll be looking at you saying 3 methods of separation to isolate this protein. Size exclusion, anion exchange, isoelectric point precipitation. Any questions there?
When would we use like separating based on the like buffer, like with the pKa and pi values? Does that make sense?
You don't separate based on pKa, you separate if you know the pi value and the charge, right? And the size. So if I give you pi values, that means you remember, oh, I need to do isoelectric point separation because I gave you the separation, the different protein isoelectric point. Okay, so that's a hint for you to say, I'm going to use isoelectric point separation. And when I give you size, that means, oh, there's size exclusion chromatography involved. And I give you charge, that's ion exchange. And if I give you negative, that means anion exchange chromatography. Okay, if you want to quantify this protein after isolation using an immunoassay technique, indicate the type of assay you would choose and explain its principle. Sandwich ELISA, that is your method. Because protein, large molecule, you have multiple epitopes. So it can be sandwiched between 2 antibodies. So sandwich ELISA, just remember the principle of sandwich ELISA. So if I want to determine recovery rate or percent yield, how much protein I was able to collect from the original amount of protein I had. So you can simply do a protein assay, total protein assay. You can use DUMAS, you can use CalDAL, or you can use even simple method because it is only a purified solution of protein. So you can use absorption at 280, or you can use Bradford. All of these methods are correct. In this case, the protein is purified. So you can use research methods. You can use absorption at 280, you can use Bradford, you can use Burette method. All of those research methods can be used. All right, you want to identify GMO in a soybean field. So you're in the field and you don't have a lab. You don't have a sophisticated lab. So what food constituents would you be analyzing for, and which analytical technique would you use? Explain this principle. So proteins, right? GMO, when you want to determine presence of GMO, you look at GMO proteins and you use the test strip method, because then you don't have a sophisticated lab. You can extract a sample of protein pretty quickly, and then you dip your strip, which is based on sandwich ELISA, that you just explained that in this question. So let me see, do I have immunoassays open? I don't. Let me open it. So this is where we explain the lateral flow strip. So you have antibodies labeled with color, and if you have the protein of interest, the GMO protein, it will bind to it, and by lateral flow, the fluid will go up to where you have another antibody for the antigen, and it basically sandwiches it, and you see a color at the test line. If you don't have an antigen, your antibodies that are colored will just also move by lateral flow and go to the control line. The control line has antibody to the antibody that is colored. And then you would see a control line color, and you do not see the test line. So here you don't have GMO, here you have GMO. Is it possible to use Western blot? No, it's a very sophisticated method. You're required to run your sample by electrophoresis and have them on a gel, transfer them to PVDF membrane, and then you wash the membrane with antibodies, and then you would have an antibody that is labeled. You add a substrate, labeled with an enzyme, you add a substrate, and the substrate converts the enzyme converts the substrate to color, and then you would see the color dot. If you don't have the protein, you don't have the antibody binding to anything, and then you don't have the other antibody, the secondary antibody binding to anything, so you don't see a color change. So this is an example question where I ask you, what could be present in milk as a contaminant of concern? And how would it make it into the food, the milk, and what method of analysis would you use? And when I say indicate means of detection, you would go MS or spectroscopy or whatever is your assay. In milk, well, if it's a milk powder imported from outside, yes, melamine. But when I say milk, mostly I mean liquid milk. So what could be there that you don't want to be there?
Antibiotics.
Antibiotics. Okay. It made it to the milk because the cow was potentially given subtherapeutic antibiotics, or the cow was sick and she was on antibiotic and was not suspended in an amount of time sufficient to deplete the antibiotic from the system. And that's how it made it into the milk. And then you can say antibiotic, we can do charm test, or we can do LCMS detection. Wheat kernel. What could be in the wheat kernel?
Mycotoxin?
Save the mycotoxin to peanuts. Wheat kernel, you could have an insect larva growing in there. So you can do X-ray to determine and count how many insect larvae are there, or how many infected kernels are there in 100 grams of kernels, 32 or more. Peanuts, you can say aflatoxin. So for wheat kernel, you can say extraneous matter, insect larva. For peanuts, you can say aflatoxin from mold growth or fungus growth. And They can be measured by immunoassay. You can explain the assay, or you can be measured by LCMS, and you explain that a little bit. Green vegetables or crop, any crop.
Pesticides.
Pesticides. Bottled water could be there. Bisphenol A, right? PBA. Yes. Deep fried potato chips.
Acrylamide?
Acrylamide. Yes. So you might have a question similar to this, or the question might be opposite. I might give you a contaminant and you might want to give me a food product that can be contaminated by that contaminant. Vitamin C and processed orange juice. So what would you use to determine L-ascorbic acid? Okay, so here is the method you want to remember. Let's see. Vitamin C. Yes. Again, you don't want to remember the structure. You want to say, okay, if you might not want to also remember the, well, it's dichloroindophenol, but you can say dye, where the dye oxidizes ascorbic acid, or ascorbic acid reduces the dye. So the L-ascorbic acid reduces the dye, and you get a reduced dye that is colorless. So basically, oxidized dye has color, and the ascorbic acid reduces that and give you a colorless dye. So you're measuring the L-ascorbic acid form. You want to remember that some processing and storage may result in oxidation into aldehyde-ascorbic acid, which is still bioactive, and you still want to be able to determine that. So what would you do to determine the amount of aldehyde-ascorbic acid? Do you remember what we do? Do the same assay?
You run it with the reducing agent.
Yes. You add the reducing agent, all of the aldehyde-ascorbic acid get converted, and then you do the same assay again. So you do it without reducing and then with reducing, and the difference will be that. The alternative method that you would use to determine both forms is the fluorescence method, the fluorometric method, which I explained here. You just say fluorometric method, L-ascorbic acid is oxidized to aldehyde-ascorbic acid. So all of the ascorbic acid is in one form now. So you're measuring both forms. And you react with the reagent to form a fluorescence. OPA is the reagent. You just react it, you form a fluorescent, and you measure fluorescence. So what are the precautions that you would need to make while preparing your sample for analysis? So it is vitamin C. And remember, vitamins are susceptible to a lot of different environmental conditions. Vitamin C specifically can get oxidized very easily, right? So it's susceptible to light, susceptible to oxygen, and susceptible to temperature. So I want to make sure no heating and not a lot of like leaving the sample out for a while until you're ready to analyze. So there's oxygen, there's light, you're going to degrade your ascorbic acid. All right, so this question has to do with titratable acidity. All right, did anybody solve this question? I haven't solved it personally. I'm gonna get my pencil and start solving. If you haven't solved it, try solving it. If you had, just tell me your answer. So 50%, meaning 50 grams in 100 milliliters. So when I talk about normality or molarity, that means in 1 liter. So I need to know the amount of NaOH present in 1 liter. So I can unify the units. So I can determine the molarity or normality of NaOH, the 50%. So this means I have 500 grams in 1 liter, 1,000 ml. If I have 50 grams in 100, I have 500 in 1,000. Okay, so now you get the number of moles of this solution. That means I have 500 grams. I will definitely give you the molecular weight of NaOH. So it would be 40 grams. So you divide 500 grams by 40 grams. You get 12.5 moles per liter. So the normality or molarity, it's the same, it's equal. Normality and molarity are equal because you have one OH. So it's 12.5 normal. All right, how many milliliters of this I need to take to produce 1 liter, say? I didn't say how many liters, but let's say I want to produce 1 liter. I will tell you the volume. So if I want to prepare 1 liter, that's 1,000 milliliters times 0.1 normal. So I'll do XV times XV. Normality times volume equal normality times volume. And then the X will be, what would it be? 5? No. 8? Yes, 8 milliliters. All right, so I would say you want to finish it. So you would prepare, you take 8 ml of the 50% NaOH solution, you place it in a volumetric flask and you make up to 1 liter. Now, how would you standardize it? How did you do that in the lab? You standardized it against a standard acid phthalate. So potassium acid phthalate. If you can remember KHP, you can say KHP. So you would get a known amount of standard acid, solubilized in water. You add an indicator, I think it was phenolphthalein indicator, and you titrate with the NaOH, and then at equilibrium, use the equilibrium equation, and you calculate the actual normality. Why do we need that? Because NaOH is impacted by any dissolved CO2 in the sample, because CO2 will react with the sodium and give you sodium carbonate. The normality will go down. And also you need to make sure that you're using the accurate normality to determine as much as possible accurate titratable acidity. And here it's telling you to calculate. Did anybody calculate that at all? So again, you use your derived equation for equilibrium, where you use the normality that is given. I gave you the normality of NaOH, which is standardized, times the volume of NaOH used. Here you have to multiply by the equivalent weight of the acid. Now, how would you know the equivalent weight of the acid? I gave you the molecular weight. And if you look down to section D, I gave you that it has 3 carboxylic groups. So I'm telling you now that you need to divide 192 by 3, basically. You will have that in the question somewhere, where it tells you how many carboxyl groups you have, so that you know how to divide the molecular weight by how many, by 2, by 3, by none. And then the volume of the sample that has been used, the correction from milliliter to liter, so you divide by 1,000, and the percentage you multiply by 100. You get 0.67%. That is the amount of titratable acidity. You forgot to boil the sample prior to titration. your value would be over or underestimated. What do you guys remember from our discussion, lab discussion? If you have CO2, overestimation, yes, thank you. So the CO2 will form carbonic acid in water. And carbonic acid buffers at pH 8.2, which is the endpoint pH. So you won't see the phenolphthalein changes color. It changes pink and then disappears again because the carbonic acid is buffering at that pH. So you overshoot the titration. And here I'm asking you to draw a titration curve. So the idea here is to remember that there is a buffering around the pKa. So when you draw your curve, you want to make sure that it plateaus a little bit around the pKa. So your pH would be on the y-axis, and then your milliliter of NaOH on the x-axis. So when you draw, so that when you're titrating, your pH goes up. When it reaches the first pKa, it kind of you draw a straight line about, and then goes up again, and then another straight line around the second pKa, goes up, and it's kind of like a ladder. So make sure you have 3 plateauing areas around the pKa. That's where you have maximum buffering capacity. And then the pH, once you reach equilibrium, the pH spikes up, and that's your titration curve. And it would be around pH 8.2, where you extrapolate the milliliter of NaOH used to reach that pH. All right, question 9 is basically another just repetition of you practicing calculations and asking you if the percentages are reasonable. What is this sample? This is cheese. You shouldn't have a lot of carbohydrate in the cheese, for example. And depending on the cheese sample, it will be high in fat and high in moisture, potentially. So you want to make sure your values are reasonable in a sense that you don't give me a total carbohydrate of 50%, for example. It can't be. What are the minerals that need to appear on a nutrition label? Calcium, iron, potassium, and sodium. How would you analyze these minerals? You can say atomic absorption spectroscopy, you can say ICP, AES, whichever you're comfortable with explaining the principle. So if you say atomic absorption spectroscopy, you want to make sure that we ash the sample, your ash is solubilized in dilute acid, you dilute so that your mineral is within the standard curve. Of the standard of your mineral that you will be using. In atomic absorption, you have flame for atomization, and then you have a light, source of light that is your lamp, that is a cathode lamp, that has the metallic form of your element. We'll give you the spectra within that element that the element absorbs light at. And the element absorbs light, and then you detect by a photomultiplier tube detector. So basically you want to remember that you have a unique lamp for each element because you have a unique cathode made up of the metallic form of that element. The flame is the source of atomization, and the source of excitation is the lamp. In plasma, the plasma is the source of atomization and excitation. Both. Okay. Any question there? This is another practice of using the Henderson-Hasselbalch equation. So just make sure you remember that equation in case you have to calculate how much volume of acid and base you need to mix to form your pH 7. So basically Henderson-Hasselbalch, pH equals pKa plus log of concentration of A minus your conjugate base over concentration of HA. And we've solved many of these before, just practice again one more time. Okay, so here is a nice question here for kind of remembering where you can use a GC versus HPLC. Here we're looking at a flavor adulteration, artificial flavor versus natural flavor. We're talking flavors. These are molecules that are volatile and they are present in very, very low concentration. So in this case, you want to go with GC. Volatile molecule and very low concentration, GC is much more sensitive than HPLC. Much to my dismay, much to the happiness of Gary. So yes, so here you go with GC analysis and you say because it's volatile molecule and present in low concentration. That's the answer because GC is more sensitive than HPLC. What kind of detector? What detector used in the lab? FID. You don't have to remember very many detectors. I know Gary went through a lot of other detectors. If you know thermal conductivity detector and FID, these are kind of the most common ones in the GC world. There are other specific ones, but just try to remember the ones, the thermal conductivity one and FID. FID you used in the lab, you had a question in the lab report about it. Just remember that you generate a flame, hydrogen flame. Your sample, when it reaches the flame, your gas, the volatile sample, when it reaches the flame, it gets ionized. And then there is a potential that is directed to the flame. And then the change in current is correlated with the concentration of the ion or the sample concentration. So you observed peaks that your standard does not include. So you decided to link your system to mass spectrometry because you don't know, you're trying to identify. So what information are you seeking with the use of MS? So we're seeking more molecular structure information. We're seeking molecular weight, potentially fragments, because with GC, you use electron impact, which is hard ionization, you get a lot of fragments. So you get molecular information that helps you in identification. If you have a library, you can try to figure out the structure of the molecular weight. Yeah, so what source of ionization? Electron impact is the source of ionization with GC. Try to remember that. You can use chemical ionization, which is soft ionization with GC, but if you use electron impact, you get more fragments, you get more information. You cannot use electron impact with LC. So LC, the most common one is ESI, which is electrospray ionization. There are other forms of ionization, of course, MALDI, ESPI, and another chemical ionization. There's so many, but try to remember electron impact is with GC, ESI is with LC. ESI is soft ionization. Okay, so immunoassay, this is a diagram. You might get a diagram of an immunoassay. This is, for example, one type of ELISA, and we covered a couple of other types of ELISA in class. So you want to know the different types. So what is this ELISA looks like to you? What type? Sandwich ELISA. Okay, so your antigen in red, you have a solid phase, the antigen reacts with the antibody, we get the detector. So we have capture antibody and we have detector antibody. It's labeled with the enzyme. It will react with the antigen, and then you add a substrate, and then you get a color product. So label the different components shown in the diagram. So capture antibody, antigen, labeled antibody, or you can call it detection antibody, the enzyme here, which is that orange, dark orange structure, I don't know. And then you have the substrate that is gray, and then you have the product that is pink. So what type of ELISA? Sandwich ELISA, explain its principle, is basically all the steps that I just covered now. Give an example application. Do not say mycotoxin or melamine or any small molecular weight. No. Small molecular weight cannot be sandwiched. A small molecular weight you can do comparative ELISA with. Small molecular weight, only one epitope. So you cannot have two antibodies reacting with it. So it cannot be protein. So it has to be protein, and you can say for detection of allergen, detection of adulteration, for example, meat adulteration, GMO, detection of GMO. Okay, so any of these three can be correct. If you say any small molecular weight, it will be incorrect. And the opposite is true. If you have competitive ELISA, you cannot say a protein. Competitive ELISA, where you use a hapten, and it's for small molecular weight components, like aflatoxin, for example, or melamine. Would a low absorbance reading indicate high level of antigen in your sample? No. Here, the more sample you have, the more labeled antibodies that will bind, the more color you get. In comparative ELISA, it's the other way around. The more antigen you have, the less label hapten or antigen will bind, and therefore the less absorbance. Okay? So opposite for comparative, and directly related in sandwich ELISA or indirect ELISA. Again, remember the difference between sandwich ELISA and indirect ELISA. Indirect ELISA is not competitive ELISA. Just make sure you know the difference. Some students get confused with these. Indirect ELISA is basically you just have an additional antibody. We call it secondary antibody. That is antibody to the first antibody. So it's really a sandwich ELISA, but the antibody that binds here on top is not labeled. So you just have to use a third antibody. We call it secondary antibody. That is antibody to the antibody. But it's basically sandwich ELISA, but indirect. And again, higher absorption means higher concentration. Okay, so indirect does not mean, some students confuse that because of the word indirect. So if some students think with higher antigen you have lower absorption. No, it is similar as sandwich ELISA. Okay. And here again, we have another protein separation. Here I give you a molecular weight. I give you that I used pH to precipitate. Then I added salt to do salt precipitation. And then I ended up with my enzyme and another protein that has a molecular weight of 18 kilodalton. So you explain the first step is to precipitate at the isoelectric point. And then we take the supernatant in this case. So the enzyme is in the supernatant, and I precipitate the enzyme with salt. I centrifuge, I take the precipitate. Now I have my enzyme, but I still have another protein in there of molecular weight that is 18 kilodalton. But my enzyme is 38. Then the last step, which is the question here, what would be the final step you would employ to separate your target enzyme? I would say size exclusion chromatography. All right, so, and in this question here, it's asking about how would you desalt your sample? So dialysis. So you want to remember your dialysis membrane removal of salt. So basically you put your sample in a tube that have a particular cutoff where you put that tube in water and the salt diffuses and you reach equilibrium. And then you change the water a couple of times every time you reach equilibrium until the salt concentration in your sample is very, very minute. And that's your desalting step. Here's another question on oil, just another thing. This is what we talked about if it was less than the specification. What does that mean? That means it might be contaminated and you might have, it's contaminated with an oil that has a higher molecular weight, average molecular weight of the fatty acid. What would you test in the receiving oil? There's plenty of things. You can do iodine value. You can look at, let's say, the melting point. You can do refractive index. You can look at the oxidation state or refinement, how refined it was by doing measuring free fatty acid. There's so many different tests from the characteristics tests that we covered in fat characterization. If after processing the iodine value was greater, that means we did not complete the hydrogenation step. List 2 other tests that you would need to carry out on the final product. So if you're hydrogenating, maybe you want to look at iodine value, you want to look to see if the final product has any oxidation. There are so many different tests to choose from. Again, it's another review for your oil and fat characterization. And this is also what minerals, kind of similar to the other one in cheese, calcium, potassium, sodium, iron. You don't have any iron in the cheese, but still for the labeling purposes, again, you choose atomic absorption or ICP-AES. Do you need to ash your sample? Yes, you do need to ash your sample because you need to get total carbohydrate. So you need the total ash and the total moisture content. You would do dry ashing to get the total ash. You would do wet ashing if you're analyzing for any volatile mineral. And that's the end of that. Do you have any questions? We can cover any questions you have. Don't be shy. It is the time for it. Could you go over the difference between sandwich ELISA and indirect ELISA? Yes. Let's go to this slide. So in sandwich ELISA, basically you have a capture antibody and a detection antibody. The detection antibody is labeled, okay, with the enzyme. And it's simple, you just sandwich your antigen and you have the enzyme reacts with the substrate, gives you a product. And the higher the absorption, the higher is the antigen in your sample. If you don't have antigen, this detection antibody will not be bound to anything. You have to remember that after every step you wash. So you wash everything that did not react with your surface. And then therefore lower absorption means lower amount of antigen. In the indirect ELISA, and most common, indirect ELISA is more common than regular sandwich ELISA because you can purchase antibodies that already labeled. If you're trying to determine the immunoreactivity of a protein that is modified by processing or hydrolysis or whatever, you get serum from human sera. So this human sera that from a human that is that has allergy to that protein. So it has antibodies specific for that protein. But it's very hard for you in the lab to take these antibodies and label them with the enzyme. It's kind of like additional steps that you have to take to label with the enzyme. So instead of having you do that, you say, okay, I'm just going to use the human sera to sandwich my antigen if it is immunoreactive, it will get sandwiched. But I'm going to use a a commercial antibody that's already labeled. And this antibody is an antibody to the human sera. So you can get goat antibody, that the goat was injected with the human sera and it produced antibody to human sera antibody. So that one is labeled and it comes with your kit. So in this case, we call it indirect because the antibody that used to sandwich are not labeled. So the antibody here that comes with your assay is labeled. And that makes it much easier on you as a person doing the experiment in the lab. That's the difference, is you have a secondary antibody. You have a primary antibody and you have a secondary antibody. And the secondary antibody is antibody to the antibody. And the more antigen you have, the more antibodies bind. The more antibody to the antibody bind, the higher is the absorption. Okay, so it's similar to the sandwich ELISA in a sense. Higher absorption have higher, meaning you have more antigen. Is that good? Yeah, I'll post this on Canvas. I'll definitely post it. It's going to be very long. I hope it won't cause any issues to post that, but I'll do. Any other question, anything at all before we go?
I just have a question about enzyme reaction kinetics. And I'm just wondering why, like when you measure the rate, measure the substrate, you would measure when the substrate is less than the.
Yes, let me open. Yes, definitely, I can go over that. Let me open. This is important question. It might show up. So let me open that lecture. Enzyme. Okay. So when you're measuring a substrate, so let's say you're measuring glucose, you want to make sure you have enough enzyme so that the enzyme is not controlling the reaction. You have an abundance of enzyme. Let me go to that. Where it says, yeah, so you need to have an abundance of enzyme. So this means the enzyme is not your limiting factor. So you want the reaction to be zero order with respect to the enzyme. That means the enzyme is there, you have enough activity, it's not limiting your reaction. So your reaction rate is not dependent on the enzyme. So zero order with respect to the enzyme. And you need to have your substrate now in diluted concentrations, because if you saturate your enzyme, then your reaction is not dependent on the substrate. You want the reaction to be dependent on the substrate so that you can determine substrate concentration. So you do not want to saturate your enzyme. Therefore, your substrate concentration should be much less than Km. Let me go to this slide here that would explain it very well. So see, here's your Km. The Km is basically the rate, well, the concentration of the substrate where the rate is half Vmax. So you see, when you have very high substrate concentration, you saturate the enzyme, and then the rate of the reaction no longer changes. So you cannot detect the change anymore based on the substrate concentration. You would detect the change based on the enzyme concentration. So you want to be here when you're determining substrate, you want to be here when it's linear, right? So that's much lower than the Km. So linear meaning it is the more you increase the substrate, you see a linear increase in the rate of the reaction. And the opposite is true when you're measuring enzyme activity. You don't want the substrate to be limiting. You want to make sure you're up here. So the substrate is not limiting factor, so it's zero order with respect to the substrate. And then it will be first order with respect to the enzyme when you're measuring enzyme activity. So you want to make sure that your substrate concentration is much higher than Km so that your enzyme is saturated. Does that make sense?
Because like we don't have any enzyme questions in the packet, I think.
Yeah, you don't. I'm not sure if the exam have it. Maybe it will, but so it's good question that you've asked that. It's good. All right, any other questions you guys might have? All right, then. I guess I'm going to let you go. If some of you have questions for me and would like to stay and have more questions for me specifically, you're welcome to stay. Otherwise, I will record this. Please do fill the teaching evaluation. I will have Rachel send you a reminder and tell you that there will be extra credit for that.
I think those might be due tonight for anyone listening. I think they might be due tonight, so just
the teaching
so everyone
evaluation?
knows. Yeah, I think it's the last midnight on the last day of instruction, which would be today.
Great. Thank you, Sam. Make sure you fill that. I'll have Rachel send an email reminder too. All right, thank you guys. Pleasure. I wish it was a better semester in terms of seeing you all more in person. Okay, I will see you on the final.
Thank you.
You're welcome.
Thank you.
Yes, you're welcome. Oh, Rachel's here. Rachel? Well, she's not. Oh, hi. Oh, that's my son. What?
She's helping. Can you hear me? I don't know. Yeah, she's helping. Wait, there's the microphone. She's helping Fan at the HPLC.
Okay. All right. So let Rachel talk to me when she has a moment. Okay. All right. So Anastasia, Kat, Shushan, Emily, do you have questions?
I'm just gonna hear in what other people are saying. I'm just gonna look over my notes.
Okay. Let's see if Emily or Kat or Shushan have any questions then. Or maybe they just are here. I'll just wait here, Anastasia. If you have any question, you can ask. I'm not sure that they are by their computer. They must have left and forgot to sign out. I'll go talk quickly to Rachel about the extra credit and be right back.
guess I have a few. Oh.
You have a question, Anastasia?
Yeah. I guess I just have two. So I guess like when discussing between dry ashing and wet ashing, I think I always get the two kind of mixed up, especially for like mineral analysis. Because like which minerals would be better with wet ashing and which ones would be better with dry ashing?
Yeah, so dry ashing, if you're doing nutrition labeling, for example, you always have to do dry ashing because you always want to get the content, an ash content that you can use in your equation to determine total carbohydrate. This is a must. If you are doing mineral analysis, let's say on your food sample without needing, it's just assessment of processing, assessment of fortification, loss due to milling or whatever, you would just, if you want to do like iron specifically, you don't necessarily need to do dry ashing, you can do wet ashing. But sometimes you don't have the capability or the training or the right hood or whatever to do wet ashing. You can only do dry ashing, and then you solubilize the ash the way we did in the atomic absorption lab.
So dry ashing is like if you want to do like super specific analysis of things, or just like in general?
No, not dry ash. Wet ashing is.
Oh, wet ashing is like for specific, but dry is for like.
If you want to do just mineral analysis, you don't care for content. Just mineral analysis, and you have minerals that are volatile, and you want to make sure you want to capture those. And if you're also, if your lab is capable of doing wet ashing, and you have the training in that.
Okay. So I guess my other question is like, I do know like for protein separation, you do salting out. There's like salting out and the PI, like the differences between the PI. How do they?
One is pH related and one is salt. So the PI is pH at which you have zero net charge. So you are basically making your protein carry no charge or no net charge, basically. So it won't interact with water. It will just interact with each other and precipitate. Yes? Just a second. Yeah? No. What? Oh, I thought you had your keys with you. Nobody has a key? Dorit is coming at 12:30 to meet with me. She has a key. Maybe she's up in her office. You don't have I don't have key to this room because it's special lock because she was in that room, so they made it special lock for that room. So I don't have a key. Dorit will have a key. Or Yob. Either Dorit or Yob will have. Okay. So say that again, Anastasia. For protein, yeah. So pH is pH related. Salt is basically you're blocking the charges on the protein. And depending on how much the protein is charged and the type of salt, there's a certain concentration that you would add and the protein will precipitate.
So if there's a question, how would I, like for salting out, would it be just like it has this charge and then another protein has that charge, and so you can?
Yeah, I would give you like hint in the question. When I ask the question, the answer would be, if you read the question carefully, you'll find the answer. So for example, choosing the isoelectric point precipitation, you see that I gave you the isoelectric point of that protein and the range of the other proteins. So you would say, oh, so I need to precipitate with pH at the isoelectric point. So it's kind of like the hint is in the question.
I'm so nervous for this.
What's that?
I'm really nervous for this. I don't know.
Well, you'll be fine. If you have understanding of a minimum understanding of things, you'll be okay.
So it's 6 questions and a bonus question.
6 questions, yes. And there will be like subsections of the question.
think that's all I have. I'm just gonna study more. Thank you.
All right. Yeah, I can. If you want to think of more questions, I can be here till 12:30.
Okay. I'm gonna think I'll leave. Thank you.